What is an alternating current? Well, an alternating current is a flow of electrons that switches direction at a constant interval. You may see it used to distribute power throughout your neighborhood. The sinusoidal waves that we learned about this year can actually be applied to concepts surrounding these alternating currents. Let's say you have a load, such as a light. The direction of the flow of electrons switches back and forth through the light. Here we have the voltage represented by V, which is the potential difference measured in volts. We also have current represented by I, which is the stream of electrons that is moving through. In the United States, the standard current is 60 cycles per second. The voltage and the current are both sinusoidal waves. Now let's take a look at the following example of a simple circuit with an alternating current as its source of voltage to explain some concepts. As you can see in the sinusoid, the potential difference is changing periodically. Now let's take a look at the voltage. The equation to represent the voltage in this example, if the wave had started at 0, is this. In the graph we looked at earlier, you actually would have had to account for the phase shift towards the left, so that would be plus pi over 2 in the equation, since it starts at the peak. So V is the voltage at the time t, V subscript 0 is the peak voltage, and F is frequency. Looking back at what we learned about sinusoidal equations, we see how this example makes sense. The amplitude would be the peak voltage, F is the frequency in cycles per second, and 2 pi times the frequency gives us angular frequency, which is a measure of rotation per unit of time. Voltage can also be represented by this equation, V equals I times R, where V equals voltage, I equals current, and R equals resistance. If we rearrange it so that we are finding the current, we get I equals V divided by R. Thus, I subscript 0, which is peak current, is equal to the peak voltage, represented by V subscript 0, over the resistance. And this is the currents equation, where I is the current at time t. Like the voltage, the current in this resistor is changing back and forth. For this example, the voltage and current are in phase, meaning that their product is non-negative and will vary between 0 and the peak current times the peak voltage. Remember when we said the standard current is 60 cycles per second? How would this apply back to the example of the fluorescent light bulb? Well, this means that the light bulb brightens and dims 120 times per second as the current goes through 0 over and over again. Since this is too fast for the human eye to actually detect, if you try waving your hand in between your face and the fluorescent light bulb, you would see the output of light fluctuating, and that means that there is an alternating current. Since we now know the voltage and current, let's talk about power. Power is the amount of energy that is transferred in an interval of time and is measured in watts. Given that P equals VI, where P equals power, V equals voltage, and I equals current, we can find that the power that is supplied is represented by this equation. Now, say you have a light bulb of 60 watts. That means that the average power consumption of that light bulb is 60 watts. So how do you find average power? Let's look back at this graph. As you can see, the midway point would be the average power, as the areas above and below it are equal. And this midpoint will obviously be half of the peak current times the peak voltage. This can also be found using trigonometry. Let's use RMS current to represent the average current and RMS voltage to represent the average voltage. By the way, RMS stands for root mean square, which is a type of average determined by squaring a quantity, taking its average, and then taking the square root of that average. This is very helpful for alternating currents because the average value is 0. So RMS current and RMS voltage are defined as such. Take note to how if you had an average voltage of 120 volts, for example, the maximum voltage would actually have to be the average multiplied the square root of 2. So the peak voltage, if the average voltage were 120 volts, would actually be 170 volts. Now what can we do with this? Well, remember how power equals voltage times current? The average power is equal to RMS current times RMS voltage, which gives us this. These average and RMS values are used instead of the peak values in Ohm's law when dealing with alternating currents. We actually took a look at Ohm's law earlier, so just as a reminder, it is V equals I times R, where V is voltage, I is current, and R is resistance. Resistance, by the way, describes the opposition to current flow in an electrical circuit and is measured in ohms. We will assume that resistance is a constant here. Thus, Ohm's law, written for alternating currents, is this, where the RMS current is equal to the RMS voltage divided by the resistance. From that equation, you'll see other expressions for finding the average power, including these. So, for the electricity that we use in our everyday life, the amount of trigonometry behind their usage is unbelievable. Maybe the next time you see power distributed throughout your neighborhood, or go to turn on that fluorescent light bulb to do your problem set, you'll understand things just a little bit better.